You know how everyone's always talking about these big language models, these LLMs, like they're the next pivotal moment in AI, right? They're doing amazing things, especially when it comes to complex reasoning.
Absolutely. The progress has been pretty staggering.
And then you hear about reinforcement learning, RL, as this secret sauce,
Yeah.
helping them think better, solve really tricky math problems, write sophisticated code. It's really positioned as the breakthrough.
It definitely is. RL is frequently highlighted as the catalyst, pushing performance beyond what pre-training alone can achieve. We've seen its impact, in mathematical problem solving and also in generating functional code. It's fueled a lot of the excitement you're talking about.
But here's the rub, the grand dilemma, the whole deal, really.
Yeah.
For anyone trying to actually build or use these systems,
Yeah.
everyone's doing it differently. It's a complete free-for-all out there.
That's putting it mildly.
You've got hundreds of different papers, maybe 1,000 different techniques,
Yeah.
all claiming to be the gold standard. But they're all using unique setups, distinct data sets, different models even.
Different initializations, different hyperparameters.
Yeah. It's exactly like everyone in New York City has their own secret bagel recipe. They all swear theirs is the only authentic one, and they'll tell you yours is fundamentally flawed.
Uh-huh.
But the reality is, very few of them can consistently bake a truly great bagel. It's just chaos. The Wild West of RL for LLMs, and this fragmented landscape, it creates immense practical confusion for anyone trying to apply these so-called tricks in a reliable way.
That's a very, very vivid analogy and accurate. The field, RL4 LLM, reinforcement learning for large language models, it just exploded with research activity, especially through 2025, hundreds of publications.
Right.
But this rapid growth, while exciting, it paradoxically led to this fragmented, often contradictory understanding. Different teams, inconsistent setups, varied data, different models, inevitably leads to conflicting conclusions about whether a certain technique even works.
Which makes it impossible for practitioners. How do you know what actually works? Under what conditions? Why?
Exactly. It's a fundamental roadblock to progress and certainly to reproducibility.
So what's the true gravitas here? What's the profound importance of cutting through all this noise?
Well, that's where the specific research comes in.
Right. This deep dive today is centered on a really groundbreaking research paper, Tricks or Traps, a deep dive into RL for LLM reasoning, part 1. And this work, it's like someone finally stepped up and just said, enough. Enough for the chaos.
You're drawing a line in the sand.
They meticulously gathered all these widely discussed tricks, the normalizations, the clipping strategies, the filtering methods, and put them under a really rigorous microscope.
Crucially, under the same conditions.
Yes, one by one, same lab, same equipment, identical conditions. It's this systematic review, a truly rigorous reproduction and independent evaluation, something that was desperately needed in this space.
Absolutely. The paper's whole mission is to dispel that noise. It wants to provide clear, empirically backed guidelines and maybe reveal some surprisingly simple yet really effective approaches to enhance policy optimization for these LLMs.
By digging into the mechanisms, right?
Exactly. Delving deep into the internal mechanisms of each technique, figuring out the specific scenarios where they are most suitable, and ultimately trying to unearth the core principles that govern their effectiveness, all through a series of very fine-grained experiments. It's about bringing scientific rigor to a field that's often driven by, well, heuristics.
And if this is part 1, Tricks or Traps, it really makes you wonder what revelations part 2 might hold. Maybe a ticket to Mars.
They could hope.
But seriously, this initial work alone promises to give us clear guidelines, a reliable path forward, and that in itself is a monumental contribution. This deep dive today, it's going to empower you, our listener, to cut through that noise, get well-informed quickly, and hopefully have some of those genuine aha moments that really reshape your perspective.
Let's get into it.
All right, let's unpack this. Let's journey back to what we're calling the Wild West era of RL for LLMs. You mentioned how RL suddenly became so vital for pushing LLM performance beyond basic pre-training. Can you elaborate a bit more on that initial spark? Why did it become such a huge deal so quickly?
Certainly. To really get it, you have to think about the limits of just pre-training alone. An LLM during pre-training basically reads a massive library of human text.
Right, the whole internet, practically.
Pretty much. It learns patterns, grammar, facts, even a sort of basic sense of truth by just predicting the next word in a sentence. And that's incredibly powerful for tasks like summarizing, translation, generating fluent text.
But not necessarily for deep thinking.
Exactly. When you get to complex, multi-step reasoning, like solving a tough math proof or debugging code, just predicting the next token often falls short. The model might write steps that sound plausible, look grammatically correct, but are logically flawed.
Or it gets the final answer wrong but doesn't know why.
Precisely. It can speak fluently, but it might not think logically in that deep sequential way needed for these harder tasks. A single early error can cascade and ruin the whole solution.
Okay, so that's the gap RL fills.
That's where RL steps in. Instead of just predicting the next token, RL adds a feedback loop based on the outcome of the whole generated sequence.
So it cares about the final result.
Right. For a math problem, it gets a thumbs up, a positive reward if the final answer is correct, thumbs down, negative reward if it's wrong. For code, maybe a reward if it compiles and runs, a penalty if it crashes.
That success-failure signal, that's what's missing from just reading text.
Exactly. It allows the model to learn from trial and error, to explore different reasoning paths, and crucially, to self-correct its internal thought process by optimizing directly for a desired outcome, like getting the right answer.
Not just generating plausible text.
Correct. This ability to optimize for the right answer is what propelled RL to the forefront so rapidly. It promised a way to get more reliable, accurate, and genuinely intelligent LLM behaviors.
And that promise led to the research surge, which, as we said, directly led to this trick conundrum. All this conflicting advice. You mentioned specific examples earlier, like different ways to handle advantage normalization. What were some of those key contradictions that really confused people?
Oh, the confusion was deep because you had fundamental techniques being championed with opposite recommendations. Take advantage normalization, its core, to stable RL training.
Right, keeps the learning process from going off the rails.
Exactly. Well, one prominent algorithm, GRPO, pushed for group-level normalization. That means normalizing rewards based on how well a response did compared to other responses generated for the same prompt, like an internal competition for that specific question.
Okay, makes sense.
But then another approach, reinforce plus ARI, argued that batch-level normalization was better. Here, rewards are normalized across the whole batch of responses you just generated, regardless of which prompt they came from.
So, two totally different ways to judge how good a response was relative to others. Right there, a fundamental conflict.
Precisely. And it didn't stop there. Think about the standard deviation term within that normalization. GRPO included variance in its calculation, which is pretty standard practice in many RL algorithms. But then a variation called Dr. GRPO came along and suggested removing variance normalization entirely in certain situations. They argued it could prevent bias, especially when reward variance was very low.
Wait, so one says definitely include standard deviation, the other says definitely remove it sometimes. That's a direct contradiction on a core mathematical component.
It absolutely is. And even how the final loss was calculated differed. GRPO used response-level loss aggregation. Each complete response sequence got equal weight, no matter how long it was.
Okay.
But DRPO, another influential method, used token-level loss. The idea there was to make sure every single token's contribution was equally considered, regardless of the response length.
So you could be using GRPO thinking you're doing it right.
Yeah.
But DPIO users are saying your loss calculation is fundamentally flawed because it might ignore details in longer answers.
Exactly. Imagine trying to build a reliable system when the blueprints themselves are constantly arguing with each other.
It really is the Wild West. No map, or maybe worse, like 5 conflicting maps, all claiming to be the true one. So the paper's core idea was that these contradictions probably weren't because the techniques themselves were inherently good or bad.
Right.
But because everyone was running experiments differently. Different models, different data, different setups.
That's the core hypothesis. Without a unified, controlled framework, it's basically impossible to isolate the true impact of any single trick. If I test a technique on a small, raw model with easy data, and you test it on a huge, fine-tuned model with super complex data, we're likely to get different results.
Even if the technique itself has merit under specific conditions.
Precisely. And this fragmentation naturally led the researchers to ask 2 critical questions. First, what scenarios are the existing techniques respectively suitable for? And second, maybe the most important one for people actually building things, is there a simple and generalized combination that can be used to enhance policy optimization across various settings?
Okay, so they saw the chaos, they framed the key questions. Now, the crucial part, how did they actually bring order? What was their systematic, almost forensic approach to testing all these different tricks?
Their approach was really commendable for its rigor. They essentially built a unified lab setup. They meticulously reproduced and independently evaluated all these techniques within a single open source framework called Rowell.
So everyone plays by the same rules on the same field.
Exactly. That's paramount. It means every single trick was tested under identical conditions, same compute, same baseline model architecture, same core optimization settings. They used proximal policy optimization, PPO, as the unified baseline algorithm.
So the core engine was the same for all tests.
Right. This ensures that any performance differences they observed could be attributed directly to the specific trick being tested, not confounded by variations in the underlying RL algorithm or other experimental factors. This unified environment was their key to cutting through that noise.
Smart. And what about the models and data they put under this microscope? You mentioned they were quite intentional about this.
Very strategic, yes. For the base models, they picked non-aligned pre-trained versions of Qwen3 4b and Qwen3 8b. The key insight here is that these models start with low initial scores but have high improvement potential.
Meaning lots of room for RL to actually make a difference.
Exactly. It lets the impact of the RL techniques really show without being hidden by an already strong starting point. But then, to get the full picture, they also tested on the aligned versions of those same models.
The ones that had already gone through extra fine-tuning?
Correct. These models already had higher initial accuracy. So the goal here was to see if RL could still provide maybe more modest, incremental improvements on top of an already optimized foundation, and importantly, how those improvements might differ from the base models.
Okay, that covers the models. What about the data? Just as critical, I imagine.
Absolutely. Data quality and how you prepare it is crucial for good RL training. They used open source data sets like SimpleRL Zoo data and DeepMath, but here's a really neat detail that shows their rigor. They removed all true-false binary answers from the data sets.
Why? That seems oddly specific.
It seems small, but it's significant. They found that models could sometimes stumble into the correct binary answer, true or false, even if their reasoning chain leading up to it was totally flawed.
Like getting the right answer for the wrong reason.
Precisely. This introduced what they called noisy supervision. It gives a false positive signal, rewarding bad reasoning. By removing those binary answers, they ensure the rewards truly reflected sound, step-by-step logic, not just a lucky final guess.
That's incredibly clever. It cleans up the reward signal, making sure it actually means good reasoning.
It does. And to test across different challenges, they also categorize the data into 3 difficulty tiers: easy, medium, and hard. Sampled from standard benchmarks like GSM-8K, Math 500, Deep Math, and assessed by GPT-4o. This let them see how each trick performed under varying levels of problem complexity.
And for evaluation, how did they measure success?
They used a comprehensive suite, 6 different math data sets covering a wide range: Math 500, Olympiad Bench, Minerva Math, even tough stuff from AIM and AMC competitions. This meant they could gauge reasoning from basic arithmetic up to really challenging competition-level math. Ensures the findings are broadly applicable.
Wow. Okay. So incredibly rigorous setup. Before diving into the specific tricks, did they get any initial big picture insights just from their baseline training runs? Anything that sort of set the stage?
Yes, a couple of key things emerged early on. First, they confirmed that data difficulty matters models tended to generate more tokens, a longer thought process when tackling harder problems. Makes sense.
Sure.
But more significantly, and this really validated their approach, they saw a clear difference between the aligned and base models. The aligned models started much stronger, as expected, but the performance boost they got from RL was actually quite modest, only about a 2% accuracy increase on average.
Only 2%.
Yeah.
So if a model is already heavily optimized, these current RL techniques don't add that much more on top.
That's what this suggests. For models that have already gone through extensive alignment, current RL4 LLM seems to offer diminishing returns, just slight tweaks. This really highlighted why testing on both types of models was crucial. It showed where these RL tricks might have a big impact on base models with room to grow, versus where the gains might be minimal on already strong aligned models.
That context is critical. Okay, let's get into the nitty-gritty then, the tricks themselves, starting with normalization. What exactly is advantage normalization, and why is it considered so important in RL, especially for LLMs?
Right, advantage normalization. It's a real cornerstone technique in RL. Its main job is to stabilize the training process and cut down on gradient variance. Think of it like this. The model takes an action, generates some text, and gets a reward signal. How good or bad was that? The advantage is basically how much better or worse that action was compared to what the model expected on average. Normalization then takes this advantage signal and scales it.
Why scale it?
Imagine if the raw advantage values were huge numbers, positive or negative. Your learning updates could swing wildly, making the training unstable. Normalization brings everything into a more manageable range, preventing these extreme updates. It smooths out the feedback landscape, makes learning more consistent.
Okay, so it's about stability. And you mentioned two main flavors, group level and batch level.
Exactly. Group-level normalization looks at rewards relative to other responses generated for the same prompt. It encourages competition within that specific context. Batch-level normalization looks at rewards across a larger collection of responses from the whole training batch, regardless of the prompt. Each gives the model a slightly different perspective on its performance.
And what was the first big takeaway from the paper regarding how these two types actually performed in their tests?
The first major finding was all about sensitivity to the reward mechanism, how you define good or bad. They found that group-level normalization was remarkably robust. It worked well, gave stable training dynamics, regardless of whether the rewards were just binary, one simply right or wrong, or if they used a wider scale like 1-1, which adds a penalty for being wrong.
So group level seems pretty versatile.
It appeared so. But batch-level normalization was a different story. It turned out to be highly sensitive to the skew in the reward distribution. When using the default 0-1 rewards, where you often get lots of zeros, incorrect, and only a few ones, correct, batch-level normalization frequently caused performance to just collapse.
Why would it collapse?
Because if rewards are sparse like that, a few successful outlier samples can totally dominate the average and standard deviation calculations for the whole batch. This leads to really skewed advantage estimates and highly unstable updates. But interestingly, when they switched to the wider scale one, rewards which gives a more balanced signal, batch-level normalization regained its effectiveness.
Wow. Okay, so this is takeaway one. A trick like batch-level normalization isn't universally good or bad. Its effectiveness depends entirely on the reward structure you choose. If you pick the wrong reward setup for it, you could tank your model's performance even though you think you're applying a standard technique.
Precisely. It totally demolishes the idea that you can just grab techniques off the shelf. Context is everything. You have to understand the interaction between the technique and your specific setup, like the rewards.
This really shows why this kind of systematic digging is essential. What about the standard deviation part of normalization? Takeaway two seemed critical there too.
Yes, the second takeaway focused on the critical and often counterintuitive role of the standard deviation itself. This directly explains why the reward scale mattered so much for batch-level normalization.
How so?
When the rewards within a normalization group, whether it's a batch or a prompt group, are highly similar, for instance, if all the generated answers are correct, or they're all incorrect, which happens a lot with easy data or early in training.
Right, the model isn't getting much variation in feedback.
Exactly. In those cases, the calculated standard deviation becomes tiny, maybe almost zero. Now remember, in normalization, you divide by the standard deviation.
Oh.
Yeah.
Divided by a tiny number. That amplifies things massively.
Hugely. It excessively amplifies the gradients. This can cause severe instability gradient explosions where the model's parameters just jump erratically. Training can completely break down, giving you nans, not a number, everywhere. It's like trying to adjust a sensitive dial with a jackhammer.
So if your rewards are too uniform, too concentrated, the standard deviation calculation, which is normally helpful, actually backfires and causes instability. That's wild.
It is, and it's a super important finding. The key discovery was that removing the standard deviation term entirely in those specific concentrated reward scenarios significantly enhanced stability and effectiveness. It just prevented those runaway gradients.
So less is more sometimes.
In this case, yes. Conversely, if you have tasks with higher reward variance, maybe harder data where answers are more mixed, then the standard deviation is larger and less problematic, and including it or not makes less difference to stability. So it challenges the standard assumption that you always need that standard deviation term for normalization. Sometimes getting rid of it is the smarter move.
Truly fascinating. Okay, so armed with these insights, group level being robust, batch level needing careful reward design, and standard deviation being potentially problematic with low variance, they tried to reconstruct a better, more robust normalization technique. What did they land on for takeaway 3?
They found that the most robust combination was actually a hybrid approach. It involved calculating the mean reward at the local group level,
Okay, so context aware for the average.
but calculating the standard deviation at the global batch level.
Whoa, okay.
Yeah.
Mixing and matching local mean with global standard deviation?
Wow.
That sounds counterintuitive again.
Mhm.
Why does that particular combination work so well?
It works because it cleverly leverages the strengths of both. Using the batch level standard deviation provides stronger normalization across the whole training batch. It helps reduce the overall size of gradients, preventing those excessive policy updates, which is especially helpful when your advantage estimates might be sparse or coarse-grained, pretty common in complex LLM tasks.
So the global standard deviation acts like a stronger brake overall.
Kind of, yeah. And you combine that with the contextual awareness of the group level mean, which figures out relative performance within a specific prompt. You get a system where the model learns more stably and robustly across different situations. Their experiments showed this hybrid approach consistently performed well, aligning with claims from other research, too. It's a great example of how dissecting these tricks leads to a smarter, more effective design. Order from chaos.
That really clarifies the normalization picture.
Yeah.
Okay, shifting gears from stabilizing learning steps to, well, enabling better learning through exploration. Let's talk about clipping, specifically this clip higher idea. PPO's standard clipping is meant to prevent the model from changing its strategy too drastically between updates, right? Keep it in a trust region. Sounds sensible, but you're saying for LLMs this can actually be a problem.
It can, yeah. While PPO's clipping is vital for stability, stops the new policy from going completely haywire compared to the old one, it has a pretty significant downside, especially for LLM text generation and complex reasoning.
What's the downside?
The issue is that standard clipping can disproportionately suppress updates to low probability tokens. Tokens the model wasn't likely to generate before. When this happens repeatedly, it creates a feedback loop leading to something called entropy collapse.
Entropy collapse. Sounds bad.
It is. It means the model's policy becomes overly deterministic. It loses diversity. For reasoning tasks, that's terrible. Imagine a detective who only ever considers the most obvious suspect, the high probability one, and never explores a less likely but potentially correct lead.
The model loses its creativity, its ability to explore different paths.
Exactly. It gets stuck in its ways, unable to explore novel solutions or branch into complex argumentative structures. It effectively stifles its own thought process and limits its problem-solving ability.
Okay, so if traditional clipping stifles exploration, how does clip higher fix this? What's the mechanism?
Clip higher essentially loosens the reins a bit, but only on the upside. It introduces a higher upper bound, often denoted epsilon high, in PPO's ratio clipping calculation. By relaxing this upper limit, it gives those previously low probability tokens more improving space.
Ah, so it allows for bigger updates if an unlikely action turns out to be good.
Precisely. The model is allowed to make larger updates for tokens it was previously hesitant to generate if the reward signal says that's a good direction. This directly fights entropy collapse by allowing more diverse exploration. It opens the door for the model to try less obvious, but potentially better reasoning pathways.
So takeaway 4, when to clip higher, suggests this isn't always helpful. It depends on the model itself.
Yes, very much so. This was another case where context is king. They found a really clear distinction. For aligned models, the ones that have already had advanced pre-training and instruction tuning, giving them stronger baseline reasoning.
The smarter models, basically.
Right. For those models, increasing that epsilon high, relaxing the upper clip, notably slowed down entropy collapse and led to consistent performance improvements. These models, having a good foundation, could actually use that extra exploration space effectively to find better solutions. They had the intelligence to benefit from more freedom.
Okay. And for the base models,
Ooh.
the raw, unaligned ones.
For the base models, it was a different picture. Adjusting epsilon high had only minor effects, and sometimes it even damaged performance.
Why? Why wouldn't more exploration help them?
Because these base models tend to have a very low policy clipping rate to begin with. They weren't hitting the clipping boundaries very often anyway. And crucially, their underlying reasoning ability, their expressiveness, is more limited. So just giving them more exploration space didn't really help them find high-reward, novel reasoning paths. They lacked the inherent capacity to effectively use that extra freedom.
So another clear case where the trick interacts strongly with the model's own capabilities. Clip higher helps if the model is smart enough to use the extra room to explore productively. If not, it doesn't help, might even hurt.
Exactly. It's like giving advanced climbing gear to a novice versus an expert. The expert can use it to reach new heights. The novice might just get tangled up.
Let's get even more specific now. Takeaway 5 talks about the linguistic impact. This sounds really cool. How does standard clipping, with its lower upper bound, actually change the words the model uses and restrict its reasoning structure? Can you give an example?
Yeah, this is where the deep dive gets really fascinating, looking at the actual text. Traditional clipping, say with a low upper bound like zero point 0.2, puts tight limits on policy changes.
Hmm.
What the researchers found, and they illustrate this really well in the paper, is that this kind of tight clipping predominantly affects connective tokens.
Yeah, good tokens.
Words like therefore, if, but, however, because. These aren't just filler, they are the linguistic joints that build arguments. They introduce new reasoning directions, set up conditions, draw conclusions.
The words that structure the logic.
Precisely, and yes, quite significantly. By allowing more room for policy updates, the overall frequency of any token getting clipped decreases. But crucially, the focus of the clipping shifts. Instead of hitting those critical connective words,
The ones driving the reasoning.
it now mostly clips high-frequency functional tokens, things like is, the a, and punctuation like commas. These words are everywhere, but they have less impact on the overall logical flow or introducing new reasoning paths.
So clipping these left critical words doesn't really hurt the reasoning structure.
Much less so. It allows the model to explore a broader range of discourse reasoning structures using those important connectives, promoting diversity in how it builds its arguments. The remaining clipping on the functional words just helps maintain basic sentence stability without squashing the model's ability to reason creatively or try novel solution paths. It lets the model think more freely in terms of language.
That is a huge insight. It's not just numbers. It's about how the algorithm affects the language and thus the reasoning.
Yeah.
So knowing this, how do we actually set this upper bound? Takeaway 6 suggests a scaling law.
Right. This epsilon high parameter has caused a lot of confusion, many people just defaulting to 0.28. But the paper found it's more nuanced. For small models, like their 4B base model, performance actually gradually improved as the upper bound increased, peaking around 0.32.
So smaller models actually benefited from more freedom than the default.
Yes, it suggests a kind of scaling law for smaller models, where giving them more flexibility really helps them learn and explore effectively within their more limited capacity, like they need that extra room to find good solutions.
And for the larger models,
Yeah.
like the AB.
For the larger 8B base model, there was no consistent improvement as the bound went up. In fact, 0.28 seemed to be a pretty good setting for them. They didn't seem to benefit from further loosening of the constraints, perhaps because they already had enough expressive power.
So again, no one size fits all.
Mhm.
The best clipping bound depends on the model's size and capability. That scaling law for smaller models is especially valuable for people working with limited resources.
Absolutely. You can't just copy hyperparameters from huge models and expect them to work optimally on smaller ones, or vice versa. Understanding these scaling effects is key for efficient tuning.
Definitely hammers home the need to know your specific model. Okay, let's move to the next set of tricks. Loss aggregation and overlong filtering. Starting with loss aggregation sequence level versus token level. What's the core difference in how they add up the errors, and why does it matter for reasoning?
Loss aggregation strategy really dictates how much weight each part of the model's output gets during learning. It influences what the model pays most attention to. Sequence-level aggregation used by GRPO, for instance, averages the loss per token within each response first, then averages those per response scores.
So each full answer gets one vote, essentially.
Pretty much. Each response gets equal weight in the final update no matter how long it is. The big potential flaw here is that in a longer response, each individual token has less influence on that final average score.
So a single mistake in a short answer might have a bigger impact than several mistakes scattered through a long answer.
Potentially, yes. Or conversely, brilliant steps in a long answer might get drowned out. It can unintentionally bias the optimization towards brevity because shorter answers make their presence felt more strongly in the average.
So sequence level might discourage complex, multi-step answers just because they're long, and token level tries to fix this.
Exactly. Token-level aggregation, used in DPO, tries to correct this. It sums the losses across all tokens from all responses in the batch, and then divides by the total number of tokens.
So every single token, no matter which response it came from, gets an equal say in the final loss.
That's the idea. It aims to remove any length bias, making sure every part of every sequence contributes equally to the learning signal. This seems particularly appealing for complex reasoning, where solutions can naturally vary a lot in length.
Okay, makes intuitive sense. So the key question from Takeaway 7, does token level, with its promise of equal contribution, actually work better across the board, for all models, all settings?
And the answer, again, is nuanced does not universally apply. Another win for careful context-aware selection. For base models, the raw, non-aligned ones' token-level loss was indeed consistently more effective.
It helped them learn better.
Yes, it improved convergence speed, peak accuracy, and robustness, especially on the harder datasets. It seems ensuring every token contributes equally really helps these less developed models learn the intricate steps of reasoning more thoroughly without being thrown off by response length.
Okay, clear benefit for base models. What about the aligned models, the smarter ones?
Here's the surprise. For aligned models, token-level aggregation showed limited improvement and was often outperformed by sequence-level aggregation.
Wait, really? The method designed to be fair to all tokens hurt the performance of the better models sometimes.
Right.
Why?
It seems counterintuitive, right? The thinking is that aligned models already have strong, stable reasoning capabilities thanks to their prior tuning. For them, the careful equalization that token-level loss provides might be unnecessary or even disruptive. Sequence-level aggregation, by treating each complete response as a unit, might actually do a better job of preserving the overall structure and coherence of their already high-quality outputs.
It's like for the expert model, focusing on the whole essay is better than nitpicking every single word.
That's a decent analogy. The optimal strategy, again, depends heavily on the model's starting point, its pre-existing alignment and strength. Base models need the detailed token-level feedback. Aligned models might do better focusing on sequence-level coherence.
Fascinating. These models really do seem to have different learning preferences. Okay, let's tackle the last trick.
Yeah.
Overlong filtering. What's the specific problem this is trying to solve?
This tackles a very practical issue in training. You have to set a maximum generation length. You can't let the model just ramble on forever computationally.
Right, got to cut it off somewhere.
But in complex reasoning, especially early in training when the model is still figuring things out, that fixed limit can cut off a perfectly good reasoning chain mid-thought.
Ah, the false negative problem you mentioned. It was doing okay, but got stopped short and marked as wrong.
Exactly. That's one problem. The other is when models get stuck in no-stop repetition, just generating junk, repeating phrases endlessly without actually solving the problem or reaching a natural conclusion within the length limit. Both of these scenarios create noise, bad data points that pollute the training signal.
So the fix is to just ignore the really long ones. Mask their reward.
Basically, yes. Overlong filtering involves masking or simply ignoring the reward signal for any response that hits that maximum length limit. The goal is to make the training more robust by removing these problematic samples, the truncated ones, and the repetitive junk from the learning process. Make sure the model learns from valid, complete attempts.
Makes sense. So what's the key finding from takeaway 8? When should we use it? Does the length threshold matter?
It matters hugely. Takeaway 8 emphasizes that effectiveness is highly dependent on the task's expected length and the chosen threshold. For short to medium reasoning tasks, using a relatively tight threshold, say, 8,000 tokens in their experiments overlong filtering showed substantial benefits.
How so?
It significantly improved accuracy and clarity. It pushed the models to generate shorter, more concise, complete responses. It effectively filtered out those truncated false negatives, forcing the model to learn how to finish its thought within the allowed space.
Okay, clear win for shorter tasks. What about long-tail reasoning tasks, where you might genuinely need a lot of steps using a much higher threshold, like 20,000 tokens?
There, the benefits diminish significantly.
Why wouldn't filtering still help remove junk?
At those much longer limits, the filtering mainly ends up removing the truly degenerate samples, the endless repetitions, the non-terminating outputs that are just pure noise anyway. It's less likely to be cutting off potentially valid, just very long reasoning chains, so its impact on improving good reasoning is less pronounced.
So its main value is really enforcing conciseness and completion on shorter tasks.
That, and there's a broader impact. It helps the model learn to distinguish between completed generation and truncated generation. By ignoring the unfinished ones, the model avoids learning bad habits from them and, crucially, gets better at modeling termination behavior. It learns when to stop appropriately rather than just generating until it hits a wall. So, yeah, it's not about an arbitrary length, but about removing unproductive noise, and its value is very threshold dependent.
This has been an incredibly detailed dissection of all these individual tricks, like taking apart an engine piece by piece. But now, the moment we've been building towards the aha moment, they took all these findings, hypothesized that the right combination should work really well, and introduced something called light PPO. What exactly is light PPO?
Light PPO is? Well, it's beautifully simple, really. That's its genius. It combines just two of the techniques we've discussed, specifically chosen because they showed robust performance, especially on the non-aligned models.
Only two. Which ones?
First, it uses that optimized advantage normalization. We talked about the hybrid, group level mean, batch level standard deviation.
Okay, the robust stability one.
And second, it incorporates token level loss aggregation.
The one that helped base models learn detailed steps. And that's it.
That's it. No complex multi-stage pipeline, no fancy dynamic filtering, no special reward shaping, just those two core empirically validated components. Minimalist.
Okay, I'm almost afraid to ask. Did this super simple approach actually work better than the algorithms packed with bells and whistles? That seems almost too good to be true in AI research.
The results were genuinely stunning, and a powerful testament to understanding over complexity. Light PPO outperformed the technique-heavy algorithms like DRPO, which, remember, uses decoupled clipping, dynamic filtering, all sorts of complex machinery.
Wow.
And it also consistently beat GRPO, which is a widely used standard. And not by a tiny margin, it was a clear demonstration of superiority.
That is incredible. How did this minimalist design pull that off, especially on the smaller models, where you said other policies tended to collapse rapidly?
The paper points directly to the careful selection of those two components and how they work together. On the smaller 4B base model, light PPO showed that stable upward trend in performance, consistently improving. Other policies hit a peak and then crashed.
Why did light PPO stay stable?
Primarily due to its robust normalization technique, that group mean batch steered combo. It effectively counteracted the instability caused by those homogeneous reward distributions we discussed earlier, where rewards are too similar. It kept the learning stable even when the feedback landscape was tricky.
And on the larger base models? And for longer reasoning?
It showed superior performance there too, and part of the reason was what it didn't include. It eliminated overlong filtering, which we saw could restrict complex long-tail outputs, especially in base models, and it used token-level loss, which we saw was highly efficient for these base model architectures, so it included the right stuff, and crucially, left out the stuff that could hinder those specific models on those tasks.
So the big message here, the real aha, is that simplicity, guided by a deep, context-aware understanding of which tricks work when and why, can lead to much better, more stable results than just piling on complexity.
Exactly.
It's not about having the most ingredients in the bagel recipe. It's about having the right 2 or 3, knowing exactly how they interact, and crucially, knowing when to leave other things out entirely. This feels like a massive takeaway for anyone navigating this AI Wild West.
It really does. It challenges that prevailing intuition that more complexity must equal better performance. In RL for LLMs, it seems careful selection based on solid empirical understanding and systematic testing is the most reliable path. It argues for efficiency, for balancing theory with practical engineering, and gives a much clearer roadmap.
And that brings us towards the end of this fantastic deep dive into tricks or traps, a deep dive into RL for LLM reasoning. We started with the huge buzz around LLMs, the promise of RL unlocking advanced reasoning.
Oh, the secret sauce.
Right. But then we hit the wall, the Wild West of techniques, the conflicting advice, the secret bagel recipes leading to chaos and confusion.
And this research, as we've walked through, really is a landmark effort to bring order to that chaos.
Yeah.
By systematically testing everything under one roof, they've given us invaluable clarity, peeled back the layers, analyzed the mechanisms, provided real evidence-based guidelines tailored to specific models and situations.
We've seen how this research genuinely helps you, the listener, cut through that noise, get informed quickly. Hopefully you had some of those aha moments too.
Like realizing group-level normalization is robust, but batch-level needs careful reward scaling.
Or that removing standard deviation can sometimes help, not hurt.
Or how clip higher really only boosts aligned models and amazingly changes the language they use for reasoning.
And that clipping bounds follow a scaling law with model size.
Yeah.
Token level loss for base, sequence level often better for aligned, over long filtering useful mainly for shorter tasks.
And maybe the biggest shocker, light PPO. Just two simple techniques, outperforming the complex giants like DPO and GRPO.
That finding alone simplicity and precision beating complexity, it fundamentally challenges so much in the field. It really underscores why this kind of rigorous, context-aware research is critical.
It truly does. It lays a foundation for more standardized, reliable approaches, balancing the theory with what actually works efficiently in practice, a huge step forward for LLM reasoning.
But as the paper thoughtfully points out right at the end, there's still a major challenge casting a shadow over all this potential progress, the prevailing trend of model closed sourcing.
Yeah, that's a big one.
This secrecy, keeping advanced models and their training details locked away, it really hinders the broader community, hinders deeper analysis, collective learning, and truly understanding what works best and why across the board.
It slows everything down.
So here's a provocative thought we want to leave you with today. If a simple, robust combination like light PPO can achieve such breakthroughs when it's tested systematically and analyzed openly, just imagine what the collective intelligence of the entire research community, open source, and industry could achieve if more details were shared transparently.
What secrets are still hidden inside those black boxes?
Exactly. What could part two of this research, or maybe just the next wave of RL for LLMs, truly unlock if we fostered significantly more transparency and collaboration across the whole AI ecosystem? Something to really think about for the future of AI.